Hello friends, in this video we're going to talk about the principal unit normal vector. In previous videos we have also talked about a unit tangent vector, all right? And we use the unit tangent vector in a calculation for curvature. So we've talked about curvature, we've talked about that unit tangent vector. The unit tangent vector is a vector that is telling us the direction of the tangent vector, right? Because it's a unit vector, it has a constant length of 1 unit, and then the direction of it is helping us to understand the curvature of said curve C. So the derivative of that unit tangent vector, derivative of t with respect to s, is orthogonal to that unit tangent vector. And we understand from a previous section that if we have a differentiable vector with a constant length, then the derivative of that constant length vector is going to be orthogonal to it. All right, we talked about that in 13.1 in our text. So dt ds is orthogonal. And if we take that orthogonal vector and divide it, or multiply it by 1 over kappa, divide it by the curvature, then we are rendering a unit vector, we'll call it capital N, which is orthogonal to t. So N is my principal unit normal vector, and this is going to be orthogonal to my unit tangent vector. So here I've pulled in a picture considering some space curve C. And at different points on this curve, say P sub 1, we have a unit tangent vector, and P sub 2, we have a similar unit tangent vector. And so I want you to notice at both of these points where those unit tangent vectors originate, we have this principal unit normal vector, which is orthogonal to the unit tangent vector. So it's meeting or originating, they're originating from each other at 90-degree angles. One thing that's really important for us to note is that N, right, our principal unit normal vector, it always points inside the way the direction the curve bends. It's always going to extend into what you might describe as that concave region. So if I were to draw this principal unit normal vector out in this direction, that would be wrong. We don't want it going that way. It's always going to be pointing into the curve. Now, this formula that's given is a little labor intensive. So I have pulled in for us a separate formula for calculating N, our principal unit normal vector. So if we have a position vector and it's a smooth curve, which means it's differentiable, then the principal unit normal vector N is defined as the derivative of the tangent unit vector divided by the magnitude of that tangent vector. And again, we said that we know that T and N are orthogonal. T is a unit vector, which means its length is constant. And if it has a constant length, then that derivative is going to be orthogonal to it, right? So it makes sense why N is equal to the derivative. And then in order to make it a unit vector, we need to divide by that magnitude. All right, so just keeping in mind that t is your velocity vector divided by its magnitude. Or rather your tangent vector, right? V being the derivative of r. So here we have an example. We're going to find t, our tangent unit vector, and n, our principal unit normal vector, given the circular motion represented by the vector r. So the first thing we'll do, I'm just going to label it in A, B, and C. We're going to find t. So finding t, that means we know that the derivative of r with respect to t is going to give me my velocity vector. And differentiating, the derivative of cosine 2t is negative 2 sine 2t I plus 2 cosine 2t j. I had to use the chain rule on the derivative of both of those components. All right, next step, we need the magnitude of v. The magnitude of v is the square root of, I'll have 4 sine squared 2t plus 4 cosine squared 2t. So squaring each of those components, summing them, and I take the square root. I can factor out a 4. That's the square root of 4 times sine squared 2t plus cosine squared 2t by the Pythagorean identity. That's equal to 1. So I have the square root of 4, or that the magnitude is 2. So that lets me know then that t is going to be v divided by 2. So I've got negative 2 sine 2t I plus 2 cosine 2t j divided by its magnitude 2. And my unit normal vector is equal to negative sine of 2t I plus cosine double angle j. So now I've got my tangent unit vector, and in order to find my principal unit normal vector, n, I need the derivative of t. So tangent unit vector right here. So for b, we're going to work towards finding n. And we know that n is the derivative of t with respect to t divided by the magnitude of that vector. So we need our derivative of t here. Differentiating t, dt, dt, the derivative of negative 2 sine 2t is going to be negative 2 cosine 2t. That would be I plus the derivative of cosine is sine, so we end up with 2 sine 2t j. And the derivative of cosine is negative, so we should have a negative in there. All right, we just need the magnitude now for this. So the magnitude of dt, that's the square root of squaring that. I've got 4 cosine squared 2t plus, I'll have 4 sine squared 2t, and this is exactly what we had for the magnitude of v, which simplifies as well to 2 by the operation we performed earlier. So for the last part, finding n, that is the derivative of t with respect to t. We had negative 2 cosine 2t I minus 2 sine 2t j, and that needs to be divided by its magnitude, which we just calculated and found was 2. So that simplifies, and I have negative cosine 2t I minus sine of 2t j. That's my principal unit normal vector. And one thing that you can do to check or to verify this is you could calculate the dot product between t and n. And because we know they're going to be orthogonal, we know that that would be equal to the 0 vector. So there we have it. We have talked about our principal unit normal vector and how to find it, as well as revisiting how to find a tangent unit vector. So we worked through that example. Let me know if you have any questions.